So this is very clearly false in Euclidean space. The quasi-geodesic you think of as being something curving, it's close to a straight line. Okay, this looks absurd, and it's one of those things, as I said, you have to work and then you can use it. So from that we can immediately conclude the following: the quasi-isometric invariance of delta hyperbolicity. Well, we look at the following lemma. So if y, which in our case is delta hyperbolic, then then for fixed Kc, K comma C, so there exists delta prime or delta hat or something such that every Kc quasi-geodesic triangle is delta hat thin. Okay, well, the idea is just a picture. It's quite easy because it's important. I just emphasized it. So we have a quasi-geodesic triangle. How does it look? It kind of bulges out. Yeah, so you have something that's curved out a little bit like this, and perhaps maybe more realistically it sort of bulges out. It's supposed to look quite thin anyway, and like this. Well, what do we know? It's close to the geodesic triangle. Okay, so it's close to the geodesic triangle, which is thin. Now if I take any point on the orange side, well, there is a point here, so that this distance is less than m. This quasi-geodesic is close to a geodesic, and this triangle is delta thin, the geodesic triangle. So this distance here is less than delta. And meanwhile, we can find another point here. Now this is a little exercise to show this. It's a little exercise to show that you can actually find another point here, which is less than m. Okay, fine. And so this I should emphasize as an exercise. Okay, and you might need some other. It's a geodesic metric space, so you have to, because our claim is only that every point in the quasi-geodesic is close to a geodesic point less than m, or maybe it's some 2m or something here, less than, perhaps it's 2m or something, some constant times m. Okay, and the conclusion here is the distance between this point and this point. Okay, so I'll call it P and Q. So distance between P and Q is less than some delta plus maybe 3m or something like that. Okay, that is triangle thin. Remember what that triangle being thin means, that any point on one side is not very far away from the other side. Now m is quite big, so it might be far. In general, delta and delta hyperbolic need not be small. It just has to be bounded uniformly. Okay, so from this the theorem follows. So the theorem now follows. The theorem stated in the beginning, which is delta hyperbolicity is quasi-isometry invariant. I'll just again call this an exercise to warn that there's a bit of checking to be done. Essentially just that we got the statements right. No more ideas are needed. We looked at a triangle in X and then looked at its image. It was quasi-geodesic triangle. That was thin. And then it follows that the given original geodesic triangle is thin. So this is another characterization of hyperbolicity. Well, an important corollary here is the following definition makes sense. Namely, a group, a finitely generated group, G is word hyperbolic if the group G with the word metric ds is delta hyperbolic. So S finite generating set. Now, a priori, I mean the word metric depends certainly on the finite generating set you have chosen, and so a priori, so does the delta hyperbolicity. But in fact, in practice it doesn't, and that's because of this theorem that, and what we saw last time, which is the last segment, which is that given two different sets, the corresponding spaces we get are quasi-isometric.